Yes, so welcome to CFAIL, the first conference for failed approaches and insightful losses in cryptology. Super excited that we're going to be starting off with some differential cryptanalysis today. So thank you all so much. Thank you to our presenters. And I will let him give his own introduction to the talk and to where he's from and if you could maybe tell us a little bit at the beginning about how this work came about and how long you've been working on it.
Okay, so I'm Nicky. I work at the National Institute of Science and Technology right outside of DC. The talk that I will give here is actually not something I did at NIST, not even at INRIA in Paris right before that, but in Belgium. Yeah, then you're going to be disappointed then. It's going to be one of your algorithms, but there's not going to be a lot of new things in here. But everybody else here hopefully will get some interesting new insights. I actually have a bit of a background in the first slides on why I think that I want to present at this conference, what motivated me to come over. So let's maybe start with that. There's a short anecdote that I'd like to share with you guys. FSE, Fast Software Encryption 2009, was the first international conference that I attended. I remember that there was a talk there given by Mitsuru Matsui, where he was discussing key collisions of the RC4 stream cipher. Really interesting presentation. He rounds up. Are there any questions? A colleague of mine, Veselin Velichkov, raises his hand, and his question is, how do you come up with all of this? And I felt like you could hear a pin drop, you know? Oh no, you just ruined your whole research career. You're not supposed to ask this question. The answer is obviously going to be something like, well, I know this stuff, right? But that's not what happened. What Mitsuru Matsui did is he gave a really detailed and structured explanation of how he came up with the initial idea and how he scaled down the algorithm in a very specific way, then exhaustively could search, because it became feasible, on a computer for any possible property, and then looked at those and said, is there any of those that I could extend to the bigger variant? And I felt, whoa, that was the best question. And I've also actually realized this myself as well, that in many cases, people are not so interested in the talk that I'm giving, not so interested in the paper, but they want to know what's the story behind it. I feel that CFAIL could be one of those conferences where you want to know what the story is, and I really appreciate the opportunity here to tell it. And of course, the gimmick that the story has to be a failure, I'll give you guys a failure for this talk. So what specific failure will I talk about? There is a paper that was put on ePrint in June of 2013 by myself, where the title was that I was going to prove that some specific cipher was secure against a certain technique, some assumptions, but that was something that even if people always thought it would be, it never had been proven, but it's not the type of proof the mathematicians would like, because you just run a computer program and nothing comes out and you say, okay, so there was no solution. But at that time, I felt like we want to have this type of result. Reviewers were quite skeptical. They thought that there might be some mistakes in some parts of the paper. At least they were not really convinced of some of the assumptions. So I just thought we do some more experiments, and then maybe it will be possible to convince everybody that the assumptions are correct. But actually, in the last one of all those experiments that I was performing, it turned out that one of the assumptions actually failed, and okay. So the paper was updated, a lot less spectacular, towards, which is the standard cryptographers speak of a failed approach. And not surprisingly, the reviewers were underwhelmed, just like, come on, fix your problem. And it never actually really got fixed. I'm also not sure if it is fixable. And that's something I'd like to talk about here. So what I want to clarify is, because this is the first conference on failures, we need a definition on what a failure is. I'm providing a suggestion for a definition here. So what I see as a failure is when I do not achieve my original goal. So what I do not think is a failure is just that I would say something like, oh, my paper didn't get published, or I didn't get, in fact, this paper didn't get published, but I don't feel that that is the failing part of the work. It's just this thing, because I had my goal that I wanted to achieve, and I just didn't get there. So let me start by some really basic stuff to try to get you a sense of what differential cryptanalysis is. So what we have here is like a real application. This is how you would open a car. There is, let's say how it doesn't work, right? If you have a signal that the key is going to send to the car, because the signal is a radio signal, anybody can listen to it, anybody can intercept it, so there would be no security. You can just copy the signal, send your own. So that's not how it works. How it works is the car sends a challenge, which is like a number, and based on this number, the key will calculate a response. And it's supposed to be that if you've never seen the challenge, you don't know what the response would be. But you could actually give the key to somebody, or like get access to somebody's key and give it a whole lot of challenges, collect all of the responses. Like I might loan out my car for the weekend to somebody. The moment that I have my key back, I would know that if this challenge is fresh, and like if it's big enough or random enough, then the challenge will repeat itself. And it doesn't matter how many challenges and responses that you have, even challenges you chose yourself, you shouldn't know any information about what the response is going to be. Now, how would you realize is if you're going to use some cryptographic building blocks? Well, you could say, I'm going to encrypt this challenge. And basically, the challenge would be the plaintext. You're encrypting under some secret key K that then only you and the car would know. I mean, the key and the car. And then the ciphertext would be the encrypted version of this challenge. And you could check to see, are these two things corresponding to each other? Is the challenge that I received actually the real encryption? If so, door opens. If not, you're out of luck. What would differential cryptanalysis be? So for differential cryptanalysis, the question is, well, maybe let's again take a step back. Let's say this challenge, this response C, so the ciphertext C. If it's not random, you probably did something horribly wrong, right? Because the key is already supposed to be random. So if the challenge is not random, like just looking at one response, you're maybe unlikely to see something going wrong. What you could try to do is say, what if I flip some bit in this challenge, flip a bit in the plaintext? Well, it could be that there is going to be some property in the ciphertext that I might detect. Okay, what does it mean flip some bit? Like I could say, flip the first bit and see what happens. Or flip the second bit, or the third bit, or the last one. Or actually any strange combination of bits I could flip just to see, would this give me some ciphertext that is going to give me like something more likely than random? And if you would have any of these properties, it's like the basic concept of differential cryptanalysis, this would be a problem, because it basically means that you would know the response to a challenge that you've never seen before. And I don't want to go too much into detail about this, but still I quickly want to mention it. The way that I've explained here how you could understand differential cryptanalysis is actually, without saying it too explicitly, linking a whole lot of different things. When you're in a university context, I see that there are quite a lot of people who focus a lot on this modeling part, and then say, okay, we have this accepted model where you have the adversaries, and they can choose the plaintext, and they will do the encryptions, and you can, if something not random is there, they can distinguish, and I broke the thing. That can be very different from how the application is working. In practice, I see a lot of mismatch when some new attack comes out, and people start wondering, hey, does this actually break the thing that I'm using? And it can be confusing because, you know, in the attack I was explaining here, you might get into the car if there's something non-random about the ciphertext, but not necessarily you might know the key. So not every attack needs to be an attack where you can recover the key. Also looking at it differently, it doesn't mean that if you are going to look at something like a known plaintext attack or a chosen plaintext attack, that is something unrealistic. I see people say, if I know the plaintext or I can choose the plaintext, what's still the point of encrypting, right? If I know the plaintext already. Well, here's an application where you can actually know and choose the plaintext and query as many times as you want because you would have access to the key. So I don't want to go too much into detail about this, but I do think it's interesting to see where you would position yourself and how you would explain what is actually going on in differential cryptanalysis. And here I'm then linking the model with the application, but also the attack. Because if you have a differential cryptanalysis attack and you can somehow see something non-random, then that breaks the application. And to go a little bit more into detail of how you would do differential cryptanalysis on actual cipher, like this AES that you saw on one of the previous slides, to see what input difference, like bits that flip into the input and so whatever difference in the output, what probability I would get here, what would be good ways of choosing these values. Typically you want to look at values inside as well, like what happens after one operation, two operation inside this cryptographic algorithm, and basically trace the differences throughout. And if it's going to be the case, like you're walking through a mountainous area, like the easiest way would be to follow the valley. Like if there's some way that is going to be much more likely or much more convenient to follow, then these would be, you would expect the easy way to get to your destination. A similar thing is going on here. But then you might ask yourself, okay, so a differential would say like how you go from A to B. The trail would say which internal parts you would need to follow. If there are different ways to go from A to B, then they might add up. And this is a way in which different roads can lead to the same destination. So how would this apply to AES? It's actually really simple. And when I was discussing this with the AES designers some time ago, they said, well, that might have been the strongest argument that eventually led this to be adopted as a standard. If you want to look at AES and say what the resistance is against differential cryptanalysis, the argument is super simple. What you have here is, as a description of AES, this plaintext coming in, you add subkey. S is basically an 8 to 8-bit lookup table. In cryptography, lookup table is S-box. And then after this set of 16 lookup tables, you do some linear mapping of this. And just start repeating this 10 times. Where does the security from differential cryptanalysis come from? Well, we need to have this concept of what is an active S-box or a non-active S-box. So an active S-box is one that has a difference at the input. That means it also has some difference at the output, because it's a bijective function, invertible function, otherwise you can't decrypt. But if an S-box is not active, it means there's no difference at the input. But if there's no difference at the input, there's also automatically no difference at the output. So for every non-active S-box, you're not actually paying in probability. You have this following with probability 1. But whenever an S-box is active, this type of S-box has been designed in such a way that the probability will be at most 2 to the power minus 6 of going from any input difference to any output difference. Actually, an interesting open question here is, could you construct a different S-box where this probability would be at most 2 to the power minus 7? And quite surprisingly, this is still an open problem, so people don't know. Haven't proven that it doesn't exist, but also never have found a construction. Now, I don't think this is like because these are difficult problems, maybe the first problem you want to work on if you look into differential cryptanalysis. But I just want to show that even if you start building it up, very quickly you start getting problems that seem to be easy, but are actually really not easy at all. The white trail design strategy is the basic argument of security against differential cryptanalysis. And it basically says, no matter what you do, for 4 rounds of this construction, so the total is 10 rounds, for 4 rounds of the construction, you will have always at least 25 S boxes that are active. So there is no way of somehow choosing a good difference at the input that will go through with a high probability, because whatever you will do, at least 25 S boxes will be active over 4 rounds. And every time an S box is active, whatever input difference to whatever output difference will have a probability of at most is 2 to the power minus 6. Again, here you have these 2 assumptions that you will need to look into. One I mentioned already, which is like when you go from A to B, are there different roads to go there? So is this probability of a differential the same as the probability of a trail? But also, when you look at the probability of this trail, I'm actually like multiplying the probabilities of every round. Is that a valid assumption to do this type of calculation? So basically, you start out with a set of values. The difference would be fixed, right? So like you look at the values of like the left plain text, and then the difference is fixed, so the right plain text will be automatically determined. For all of these values of the left plain text, when you say, I want to get to the next round, how many plain texts are left? It will be some fraction, because it has to follow the difference that I'm specifying here. And then the next round only, again, a set is left and then a smaller set. So in the end, what is left with what you end up, that will be determining your probability. But when I say, let's take everybody in this room, right? And I would say, let's divide yourselves into people who are shorter, people who are taller, like go to the left side, go to the right side. And then make a second division, okay, people who are lower than the average intelligence of the room and higher than the average intelligence, you know? When I start separating people in this way, am I allowed to say that I will end up with like half and again half, 25% of the people left, or maybe more or maybe less? If these 2 traits that I'm looking at are not actually independent, then the fact that I said, oh, I assume that this is independent doesn't actually hold. So let's look here at this framework that is discussed in the ePrint paper in 2013. The idea was to look at trails for ARX ciphers, and the next slide I'll explain what that is, to find some like easy technique that needed to be automated to look for certain types of properties, eventually look for optimal trails if we can find them, check these assumptions, and then it's going to be applied to some cipher that at least one person here has heard about. And then check, like, do these assumptions hold? That's the idea. And what is ARX? ARX are ciphers, different from AES. AES was based on this idea of you have your S box, this lookup table, and your linear layer. These ARX ciphers, they only consist of 3 operations. And these operations are addition, modulo 2 to the power of n. So if it's like 32-bit addition, then just whatever bit goes beyond 32 you throw away. XOR you could see as like addition just on bits, like whatever carry you have on every bit you just throw away. And then rotation will rotate your words by the number of positions that you are looking for to move on to the next step. Like without this rotate, there's no way of having some difference in higher bit positions to go to lower bit positions, because additions only move the carries upwards. But with these 3 operations, you can build a cipher. And there's actually quite a lot of designs that have used this approach. In software in particular, these can be extremely fast. And you don't have to worry about things like timing attacks or other types of things that might go wrong, because typically each of these operations take the same amount of cycles. Usually just 1 cycle and even 0. Okay, so here, I guess for people who are just flying in from outside of the US, because of the welcome reception, Allison picked up the tab. Maybe you have not yet had the pleasure of figuring out how to calculate the tip when you go to a restaurant. Basically, whenever you are ready to pay, you get at least 3 different pieces of paper, so you have some time to practice. And you have to figure out in your group together what the tip is supposed to be. then add it up. I don't know who thought of this, because especially after a lot of drinks, I don't know who can still do mathematics. And don't say use your phone, because whenever you're using your phone, well, then you make mistakes because you type in the wrong number and the calculation doesn't add up. But anyway, so the calculation in the example that I need to look at always needs to be the right one. I mean, computer doesn't make mistakes. So here also, the calculation is correct. But it turns out to be that the people in the party are disagreeing, perhaps, about the tip amount. This person is saying tip nothing because the waitress was too friendly, apparently. So how would I adjust my tip amount? I could say like, okay, let me make this 0 a 6. Like I could do this, like extend the line a little bit so it doesn't look like you're doing something wrong there. And now what happens is I changed one digit in the input because I'm adding two numbers. What is going to change in my output? Well, we can see like at least one digit, so always in the same position you will see at least there a change, not to the right, but then in the position after that, you could have changes as well. Like in this case, what I have is that because I made the 0 a 6, the 20 becomes 30. So I have another digit that I need to change. Now, like to try to map this into what we're actually doing with differential cryptanalysis, you'd have to look at some type of calculation that you're doing where there is like an amount you can't read anymore because your paper has been smudged. So you want to calculate with this amount you don't know somewhere in the addition. If I change some number there, what's going to happen in the output? So I'm just showing you this here to get a bit of this intuition. You get a change in the same position, and in higher positions, you will get a change with some probability, depending on what the inputs are. So if that intuition works, then maybe this example will be a little bit understandable. And looking here at the paper that was published at ISIS 2003 that analyzes one of these ARX algorithms called T. And what's going on here is you have this addition, it's a 32-bit addition. What I'm giving here are the bit positions, numbered from 31 is the highest bit and 0 is the lowest, least significant bit. Which bit positions contain difference, like where I'm flipping a bit. What I'm apparently doing is flipping 4 bits in the input, no bits in the second input, I'm adding two numbers, and then I'm saying I need the same bit differences in the output. So actually what that's saying is, I want the differences in the same position, which as I showed is always going to happen, but I don't want them into higher positions. So to say the difference does not go to the next position, we're calculating on bits. This holds with probability 1/2. Like if it's not immediately intuitive, you can work this out for yourself to check. So basically what I'm losing here is a probability of 1/2 for each of these bit positions, except for the highest one, because for this highest bit position, I don't have a bit 32. So I don't care that the difference is not going to spread because like it doesn't exist. So then this will hold with a probability 1/8. Okay, I see a lot of people are still with me, so let's make it a little bit more complicated. Here, actually you're doing an addition twice in this paper. And in the second edition, you're again adding something that has the differences in these positions. And now in the output, you have no difference. Okay, like that might sound a bit strange, but that can happen, Like here, if I adjust both the subtotal and the tip amount, it can be that I still end up with the same final amount that I am paying. So that's apparently what's going on here. And also here you have a bit of a similar thing going on where to prevent that these carries will propagate, every time you have a probability of 50%, except for the highest bit position. So this gives you a probability of 2 to the power minus 3 for the second part. Okay. So you would say, okay, I multiply these two, so then I have probability 2 to the power minus 6. And this could be the probability for the two additions together. But in this paper by Hong et al., they said, we actually did some experiments, and we found this probability is higher. And they calculated that instead of 2 to the power minus 6, it's something along the lines of 2 to the power of minus 4755 and some other digits. Okay, but is that the exact probability? I actually have a paper where we looked into how you would calculate exactly what the probability would be from a 3-input addition to an output. And very surprisingly, the tool was saying, oh, the probability is 2 to the power minus 3. And once you see that, it immediately makes sense. And you shouldn't have done this whole effort to begin with, because what is going on here? A plus B is C, right? Let's say we have 3 inputs, so we have A plus B plus C equals D. Then if you are swapping the order of the inputs, so instead of saying A plus B plus C, you do A plus C plus B, the addition is the same. You can add up the numbers in any order that you want. But when you would do that, then, so I'm swapping these two values here. When you first add the second thing and the third thing and then the second thing, then the first addition is one that we recognize, one that has probability 2 to the power minus 3. And the second one is one that is no input, no input difference, no input difference, so automatically no output difference. So just by using commutativity of the addition, we could just see, yeah, of course, this is going to be a case where the probability is 2 to the power minus 3. Now you might say obvious, but when you want to analyze big ciphers that use a lot of additions or rotations, XORs, where are all these effects going on? And apparently I was trying to say, let me just multiply all these additions, but it can easily fail and make a big difference with respect to what calculation you're doing. Okay. I want to explain a little bit first about automated techniques before I pick up this example again. Basically, instead of trying to look for this by hand or trying to construct some mathematical proof that there will be a certain best way of input difference, output difference, what you could do is just write a search program. That is something that at InScript 2011 I showed how you could do for ciphers based on S boxes. There it turns out to be quite efficient if you use integer linear programming formulation of your problem, and then just a fraction of a second it tells you, here, 25 active S boxes or whatever number you are looking for depending on the number of rounds that you have. This is something that is now used really a lot, and maybe also explains why this is my highest cited paper. Apparently it's caught on like wildfire. People who want to find out how many S boxes are active like to use this style of approach. But then that's based on S boxes. As I explained, these ARX ciphers, they don't have these S boxes, so you might need a different approach. And it might be difficult to deal with some of the problems when you want to look at independence of these probabilities. What is proposed in this ePrint paper in 2013 is to say, well, instead of using this mixed integer linear programming, we could use a set solver instead. And this set solver will turn out to be an efficient way to look for optimal differential trails. So what's the technique? First, maybe give a little bit of a background of what a set solver is. Basically, you have some Boolean equation, and you want to see what are the variables that will satisfy the equation. Now, if you use a set solver, and if it's like a complete set solver, then whenever it says, I found no solution, it means that there does not exist a solution. So that's something you can use in cryptography, because then you can say, okay, apparently there doesn't exist any way of satisfying this, so I learned something. But it upsets a lot of mathematicians, because they would say, well, is this your proof? You just write a computer program, nothing comes out, and that's, yeah, but that's actually what you're guaranteeing with this type of construction. You have to start checking if you actually programmed it well and use the right set solver to see if you did it correctly. Another thing I want to mention about these set solvers is that there's actually quite a big difference between the old style way of doing it and the new style way. Old set solvers were basically just doing assignments and then seeing what results from them and doing different assignments and so on, trying to satisfy the formula. New set solvers, recently since 96 for example, what they do is they solve problems in quite a similar way that a human would solve a problem. You want to solve a Sudoku or something, you make a lot of restarts, because you might have started in the wrong way. But whenever you restart, you don't start from zero, because as you're trying to solve the problem, there will be new things that you learn. But like the clauses that you learn might be something like, I see that A is always not B. Like that's some new information that I got. So all this information that you learn, you will take along when you restart your program. And this turns out to be a really efficient way to run a set solver. And maybe, I don't want to go too much into detail about set solvers. In recent years, there has been a breakthrough that set solvers can also be done in parallel efficiently. So then this really starts to become a very powerful tool. How to apply such a set solver to differential cryptanalysis of these ARX ciphers? Well, you would need to have a way of representing the probability of your trail with a certain set of formulas. For every operation, that's easy except for the additions. For the addition, you need to do something special. There is a formula by Nicky Mouha on the next slide that will be used to calculate the probability there. And then the idea is, let's just multiply the probability of all the additions, which I already showed is not going to work. However, we'll apply it to a cipher that might avoid the problem. And then we will, because the set solver doesn't look for an optimal solution, we'll say, find me a solution with this probability. And if it says, can't find one, okay, find me one with a probability that is slightly lower, and slightly lower, and slightly lower. Like you can gradually start increasing this. And this way actually get, hopefully, the optimal solution, the best trail that came out of this. So here's this Nicky Mouha formula. It's actually representing all the more difficult cases that you could look into of this, what bits and inputs and outputs can I have different and what probabilities are going to result from it. And the nice thing about this formula is that it involves easy operations on bit level. So it's something that can be represented efficiently in as a satisfiability problem. And then just like add up all the operations that you have in your cipher to look at the total probability. Actually, I look at the weight, which will be minus the log 2 of the probability, because then I can just keep all the numbers nice integers, and it also makes life a lot simpler. I'm going to apply this to the Salsa 20 string cipher. Why the Salsa 20 string cipher? It actually has a really interesting property that, to the best of my knowledge, only one other ARX cipher has, which is called LIA. And the interesting property is, if you look at this construction, so this is only one part, there's a lot more of this copied going on, rotating, reusing. Like this is one of the basic components. If you look at the additions, and you look at the outputs of the additions, there is never an output of an addition that is directly going as an input into another addition. So this problem, a few slides ago, we were looking into, hey, I have the output of addition going into the next addition, and like it doesn't appear to hold that these probabilities are independent. Perhaps that is a problem that we don't have to deal with this Salsa 20 cipher, because for Salsa 20, whenever you do such an addition, you rotate the result and then XOR in some third independent thing. So this might have the effect of basically whitening, re-randomizing whatever values you have. So some property that might be there that would mean that you cannot multiply independently might be something that is broken by this type of structure. So that could make it easier to analyze. Perhaps that was the assumption. So what is this cipher actually? It's a stream cipher designed by one of the famous people here in the room that is submitted to the eStream competition organized by eCrypt, and that eventually got to be included into the portfolio as one of the finalist result of the competition. And as I explained, this core of the operation is going to be these quarter round operations that don't have an addition going into another addition. But you have a lot of this going on to eventually do your computation. I'm also cheating a little bit here because in the beginning I explained what a block cipher is. This is actually a string cipher. And if you look at the internals, perhaps you could say that Salsa 20 is more like a hash function even used in a stream cipher mode. There's a lot of different types of primitives you could look at. But the basic idea of differential cryptanalysis remains the same for all of these constructions. You'll always have some place where you want to know, if I flip some bits, can there be a way in which there will be something not random at the output, and that's what I am interested in, that's what I want to look at. Okay. So when applying this to this Salsa 20 cipher, first, to gradually increase this weight, which was gradually lowering the probability, first, I looked at 3 rounds of this Salsa 20 stream cipher and then said, well, give me something with a weight less than 18, so a probability higher than 2 to the power minus 18. Don't, like this is something technical, don't look at trails where all the bits in the most significant bit position are going to be flipped, because this cipher actually has a property when you do that, then also all the most significant bits will be flipped in the output. But then there's an explanation of why that can never lead to an attack, so it's like the property we don't care about. We care about any type of trail that is different from this trivial trail. And then running on antiquated hardware in 2013, after 23 minutes of computation, the computer says no solution. Which is great. You know, like normally we say no solution is a disaster. But in this case, no solution is a good thing, because it means there is no trail with this probability that exists. So that helps to do a design of a cipher. I actually didn't just try 18, it was like 16, 17, goes up. When you do choose 18, then there is a solution that you find. And the set solver can actually nicely give you all of them. There are exactly 8 trails that you will find with this probability. You could look like, okay, what about trails with like a higher weight to really get an understanding of what the cipher is doing? Then I looked into this as well, and you can get the weights of the trail and also the number of trails that you will find for this corresponding to this particular weight. So this gives you some insight into how this cipher is actually dealing with difference at the input leading to differences at the output. Something that took 18 hours to calculate, but already I was getting results in the beginning. So like it made sense to keep the program running and let it spit out more. There's like a big problem that people have when they try to use these automated techniques is just you input everything, you click start, and then you wait for days, weeks, months, nothing comes out. And you need to rethink your strategy because the tool just doesn't see whatever structure might be in there. Maybe there's nothing that the tool can exploit to find a solution. But in this case, because solutions are coming out, you can start estimating how long it might take to do a computation and how you want to analyze the behavior of the cipher. Okay, first question. I have these 2 assumptions. Do they hold? And I did a lot of experiments with like small-scale ciphers, thinking back of what Mitsuru Matsui was doing. Okay, try it on a small-scale version and see if something is going wrong there. I did a lot of experiments where you look at variants of the cipher with certain types of weights and combinations of inputs. After the review comes, like, okay, let's look at more cases, let's look at more examples and see if this holds. The set solver can do this just to say, like, okay, given your input difference and your output difference, I can tell you any way, any path from getting from this input difference to output difference. And then I can also tell you if there were different ways to go from input to output, because that means your probability is actually more, because they're clustering, they're adding up from different roads that lead from the same origin to the same destination. Okay, so if you look at the weight of the trail, so corresponding to the probabilities, then for weights of 18, 19, 20, 21, 22, 23, 24, you don't see any effect at all of clustering. So always there will be exactly one way for all of these trails that you find to go from this specific input difference to this specific output difference. However, when you look at weights 24, 25, 26, there do turn out to be a few alternative roads. So, well, it's not reducing the probability too much, but it is reducing the probability, and if we want to be honest and say, we want the trails to be optimal, so we were always assuming that this effect was not going to hold, then what we have to say here is fail. I mean, I should point out the failures, because if the talk looks too successful, it's not suitable for CFAIL, I think. So this is the first failure here. The assumption is failing here, but it's failing only slightly. Here's actually an example of what is going on. People might enjoy this. I mean, once you actually get the tool spitting something out, you could say, okay, let me take the cipher and see what bits to flip or how these bits behave and what happens eventually. Here is such an example of where you can have two different ways of going from the same input to the same output. So what's going on here is like the left side is one way of going from input to the output, actually continues on the next slide. And the right side is the other way. So you can see the top left is the same as the top right. These are the same input differences. On the next slide, the output differences are the same as well. But there turns out to be, for this specific combination of input differences, some way of saying, let me allow my carry. So I'm looking here at this the second addition. Let me allow this difference to be not just in bit position 17, but also in bit position 18. And then when that's the case, that turns out to be the best way, highest probability way of getting there. But I could also not have this difference there, then continue through, and then eventually cancel it out again and have like a different way of getting to the same output difference. You really have to sit down and check and calculate the numbers to see what's going on here. A second question would be, okay, I had this assumption of, are my probabilities independent? I thought they were. All the examples showed this. I knew definitely when an addition is going to be output and then input again into another addition, I might get into problems, but here maybe I'm okay. So I did some simulations on this as well. Let's see what the results are. So I have a lot of different trails that correspond to certain differentials then. And I want to check what the weight of these differentials is. So I have the theoretical weight, the one that the tool is giving me, and the one that would actually, that I'm actually trying to estimate from the experiments that I would be performing. And I find like I have all of these. If you look at the p-values, they are well within range. So it gives you confidence that you've actually really theoretically estimated the probability correctly of what your cipher is supposed to do. But then I found that there are actually some cases where the probability is not correct. And in one case you see, oh, this difference turns out to be impossible. That's fine. If it's impossible, it's fine. But the other is, this difference turns out to be, this differential have a probability that is higher than what I expected. Oh, that might be a problem. So I think we have to say again here, this is a failure. So what's going on here, without going into the details, basically, I thought, okay, every output of an addition is not going to be used into another addition. But there's another effect that also goes on. The inputs of the additions are being reused. And when the inputs of the additions are being reused, what this first addition is doing, look at the left side here, this first addition is saying the bits in positions 25 and 24, they need to be different. Like if one is a 0, the other needs to be a 1. Like, I mean, they can be of the same sign. And then for the next addition, I need the same condition to continue on this bit. But it's the same bit. So it's already automatically satisfied. So I thought I would pay in probability because I'm going to do another addition, but actually I got this one for free. And then in the other case, like on the right side, you see one where the probability turns out to be 0, or weight infinity, because this is something that cannot happen from this input difference to this output difference in this specific way with the internal differences. And the reason is that here, if you look at the signs of those differences, they need to be exactly the opposite for the first edition and for the second edition. So we know what we need to satisfy for the first one is exactly what we don't need for the second one, so this can't happen. Okay. So here is some discussion on what is going on. A first thing, and maybe an interesting thing, a reaction that people had was, why would you actually do this technique? Because this is not the typical way you would analyze ciphers. It doesn't make any sense to do something so complicated when actually we have good techniques from coding theory that just say, let me assume that whenever you have differences in bits, the easiest way is just not let them spread all around, but just keep them into the same bit positions, let them not go too far, because that might just blow up. And then say, give me, with tools in coding theory, the lowest weight code word, basically corresponding to give me the trail that gives me the best way of going from any input to any output difference. And this is something that just takes seconds. It doesn't take half an hour like the calculation that is done here. And also the calculation is exactly the same. Like the output is the same. You just find the exact same trail. So why did I use this more difficult technique to come up with same answer? Well, you could say, okay, is it really the case that the differences, when I keep them in the same positions, that these will be never let the second digit or the higher digits change? Is that really going to be the best trail? I don't know. And also, it only finds you trails of the lowest weight. Like if you want slightly higher or different properties, it's not something the technique would give you. So perhaps we're getting something extra by using this approach, even if it does take a lot longer to calculate. Another thing is that I've seen that there are different types of schools of thought in cryptanalysis, where a lot of people just don't check their results, and they say, like, I have some way of estimating my probabilities, and this is my result, and I assume it's going to hold in practice. I can't calculate it anyway because it's an attack that might be close to generic, but still enough to be considered a break. But then there's a problem in a lot of papers that the assumptions that are made might not hold in practice. And when the assumptions don't hold in practice, then this is something that might invalidate your results. But there seem to be other people who are focusing a lot on experimental results, and they just want to say, I don't care about what the math or estimates are, I just want to do my simulations and check what probabilities are and do everything based on experiments. But they actually also want to argue that there's a problem, because you always do a limited number of experiments, and whenever something doesn't exactly match some rough probabilities you were calculating, I do think people are brushing it away too easily and just saying, oh yeah, we got lucky, or well, apparently we just need to do a bit more. So it's actually not just two people. I find that these can be two different reasonings inside the head of the same person, or in discussions that it's easy to get confused between these. I would like to argue that we maybe need a bit of both, that it's very important to have good calculations of how your probabilities are, important to check whether they hold, and then important to update your model again if you find out that there's something that didn't actually match what your probabilities were. Another thing that might be interesting to people here, I don't know, is that if you look at the Simon and Speck block ciphers that are designed by the NSA in at least 2012, maybe early, because 2012 is the first time that designs were publicly announced. These are ARX block ciphers that are designed for lightweight cryptography. This presentation describes a technique for the first time using a set solver approach to find optimal trails, which was done and released in 2013. Now, if we look at the paper by the Simon and Speck authors, by the NSA, explaining the design of Simon and Speck, released in 2017. Now what it says in this document is, the design team used standard techniques that I mentioned, Matsui's algorithm, SAT and SMT solvers, to determine optimal differential and linear paths for Simon and spec. So this would mean, and it actually seems likely, you know, there are quite a lot of people in the NSA that have a huge amount of expertise in set solvers, in optimization technology. It seemed like a logical thing to start looking into how you can use these types of techniques to look for trails. But then basically, this would be a technique that the NSA had already used to design the cipher that was then rediscovered in this ePrint paper. Now, I don't actually have a conclusion slide. I thought a lot about what to put on a conclusion slide. What I do have is not the conclusion slide. So yeah, please keep this in mind. Whatever is going to come here is not the conclusion. So the first bullet point is not the conclusion, is the tool finds optimal differentials. I don't think it does, because you have these two fails in there. So it's not finding necessarily optimal differentials. It could be that they're actually optimal, but we can't say that they are, I think, because it would need to be, you need to do a more strict analysis and take more of these effects into account to really say that you have this confidence that they are optimal. A second not conclusion is that the tool has no use. So even if it does not find optimal differentials, it does turn out to be an extremely useful thing to start analyzing your cipher. And once you see things going on, you can do these experiments, you can go back and try to check, and the tool has been used to analyze, to design quite a few ciphers. So even if you didn't get optimal differentials, it still allows you to understand the problem a whole lot better, and that helps in designing. And then third thing is that we also do not conclude that there's a fix here. So it might be that it's possible to fix it, maybe not. Even then, I wouldn't be comfortable anymore to say that it's actually fixed, because you'd just be saying, oh, I found something going wrong and now I solved that, maybe there's something else going wrong. Like, it does seem to be that these way that we look at probabilities might be something that is not so well understood. I've also seen that, you know, people are telling me that they want to fix it, or actually like asking me when I have fixed it, or saying that they have a student that I can work together with who I can just explain, they will find a solution. And I'm not actually convinced that this is something that is fixable. I'm really not convinced it's fixable. Perhaps we can keep getting closer and closer and closer to understanding the problem. I'm not really convinced that we can get all the way there. So then going back to the beginning and going at CFAIL, what are failures, what is going on in this conference, I gave as a definition that I feel a failure is when you are not achieving your original goal. But then now reflecting on this again, is it actually not the case that in many, if not all papers in cryptography, you are short of achieving your original goal? But if that's the case, then it would actually mean that every paper is a little bit of a failure. And then I think it's useful to have conferences like CFAIL here. Anything can fail, but not CFAIL itself, I hope, as a conference. And I do appreciate your time and attention here to listen to this presentation, and I'll be happy to answer any questions.
I do have one question.
Yeah,
yeah, so it's interesting to think about how this feedback between designers and attackers, and they're often the same people even looking at both of this. So I see your point about how, you know, the tool is being used by designers in the sense of, like, you know, at least checking against the kind of things that it finds. Do you think there's further lessons for designers here in the failures of the assumptions specifically? Is there some kind of implication for design in whether it's good to put these additions near each other or not? Are there some additional lessons there?
That's a good question. I think the basic problem that we were facing here is not actually that these problems that we find in the ARX ciphers do not happen for the ciphers based on S boxes, like AES, but for the ciphers based on S boxes, like AES, there was a lot more understanding of the ways in which it went wrong. Specific structure, like these round keys that you're adding in after every round, they would be randomizing the outputs of the rounds. Then again, you assume that you can multiply the probabilities. There was a lot more structure, a lot more ideas behind it of saying, this is how we do the construction with the proof of differential cryptanalysis, automatically added by the way that we build things. For ARX ciphers, people felt, at least to my understanding, that there was not a lot of confidence. These ciphers, like when you start adding in a Boolean operation, still more or less ARX, you have MD4, MD5, or SHA-1, which were broken. I do think, I explained a bit more in the paper for those who are interested, the problems that went on there. I do think that we just didn't know, or the field didn't know, how to calculate probabilities accurately, how to go from some input difference to some output difference. A lot of results had problems. A lot of practical designs were broken. And if we had this knowledge and started building up more fundamentally what these ciphers are about, we could start bringing the understanding of differential cryptanalysis of ARX ciphers closer to the understanding of differential cryptanalysis of S-box-based ciphers, and not start seeing them as two completely different animals. So for designers, I do feel that the lesson was, we can feel confident about this, we can reason about this in similar ways that we did for other ciphers, and we can start designing ciphers for which we actually have a better understanding of what the security margin is. Because all of these ARX ciphers were typically either over-designed or completely broken. Because nobody knew how to place the rounds, especially if we're looking 15, 16 years ago. So then it may not be surprising that the field didn't really know where to go with this. Now I do feel that we have a lot more understanding of what design of these ciphers is. Yeah, Tanya?
So you said that you don't think the tool can be fixed to actually do the little things. So does it mean that you don't believe the NSA actually could find the optimal trails for Simon and Spec?
That's a good question. It's all about the wording. So when we say optimal, it's optimal under a set of assumptions, right? But then people will say, oh, but I don't trust your assumptions, and why should you be making these assumptions in the first place?
Well, they were not very specific what they assume, right?
That's true, that's true. But like the idea is, you can have a trail where you are looking at each of these operations independently, and you multiply the probabilities, and let's hope that somehow there are not too many bits different. Because whatever bits are not different, they might be random, independent, those are the ones that actually help. Your cipher is generating randomness, they help these assumptions to hold. So if you want to have this theoretical confidence, where you want to say, what is really optimal? What are my, could it be that there is another way of actually allowing more bits to be different and somehow ending up with a better result? Like a typical cryptographer would say, well, of course not, I just see it immediately. And a typical mathematician would say, well, I don't care about your proof because you just ran a computer program and nothing came out. So this is something in between where you want to say, I run a set of tools to gain a level of confidence, but perhaps that confidence was already there. And I think we do have that confidence there, that probably the trails we have for Simon and Spec, so many people have looked into them, are probably optimal and the ones that are resulting from the tool. But if we really want to move a level further, we're not at that level yet, I think. I don't know if that answers your question. Dan the man?
A more superficial question about your timeline regarding 2013 and NSA.
Yeah.
I'm remembering that NSA published this in the summer of Snowden rather than 2012.
What's the first paper that mentions Simon and Spec?
Mentions, I don't know, but I remember the publication from like June in the summer of Snowden, which would be June 2015.
Because it's a really strange story, yeah? First, there's a paper written by Daniel Engels and Marcus Sarina, submitted to your conference actually then, Directions in Authenticated Ciphers, on a do-it-all RFID requirement. And this paper says the NSA has designed a cipher and is great for Internet of Things. And it has a citation saying, here's this NSA cipher. Just, we know there's a cipher, we don't know what it is, we don't know what it looks like, we don't know how fast it is. A bit late.
The marketing department came up with the Simon and Spec name, so not that they actually had it. I guess I'm
A
also.
bit later, this is a good question, right? A bit later we got the benchmarks. So we have a cipher with benchmark, we don't know what it looks like. And then a bit after that, we got the actual algorithm. And even later, the security analysis. So everything came out in chunks. And this is when the cipher was already designed, because it was referencing a paper that was not yet public that describes the design of the cipher. And then gradually more information came out.
I guess still on the same point of whether NSA could have done something based on this 2013 presentation of yours, or paper. There were some reports that NSA has been systematically breaking into a lot of computers, like CFAIL's computer. Do you remember when you first told your computer about the technique?
That's a good question. Yeah. If they did break into my computer, I don't know how I eventually ended up here in the US, because if this all was on there. But okay, so now I arrived here at Columbia University, and I did not have anything on my computer before 2013 about this. Everything was in notes, because I was still trying out things that made no sense at all from that point of view. Like, I didn't even start doing the first experiments until beginning of 2013. Before 2013, it was just a list of problems that were bothering me without any relations to using a set solver to eventually start to get these techniques. But it is possible that the NSA actually has a time machine to go back in time to look at the paper as it was published and then not change their design. That is possible. I don't rule this out.
And on that note, let's thank our speaker. We'll take just a couple of minutes to switch the talks if you need to go.